Welcome back to Chapter 20. In today's video, we will tackle optimization, we'll give it as good of a treatment as we can in a short video presentation. The truth is, every optimization problem is going to be different, so while the general strategies we discuss here will be true for all of them, I will not pretend that this video is all-encompassing and shows you every single situation you may need to look out for. So basically the idea is in optimization is we want to optimize some sort of function, and what that means is we're going to look for the maximum or the minimum. We talked about this in chapter 19 with finding the maximum and minimum of a graph. It's going to be the same idea here. There's basically three ways we could do this. Could use technology, although that's unlikely to be the case because that would be like super easy. Maybe you'll get some problem on paper 2 that'll ask you to go through this process. If we're dealing with something that happens to be a parabola, then we should easily be able to identify that the max or the min should be at the vertex, or at an endpoint if we happen to be dealing with an interval. And but the big idea here is we want to be able to use calculus, right? So this could be a paper 1 question. I think probably more likely to show up there. If you're studying for AP Calc, optimization is one of the big free response templates that you want to really know. Very good chance that an optimization problem shows up somewhere in an AP Calc exam. If not in part 2, definitely in part 1. Not as definite of a thing for IB, but still a very important topic to look at. So let's do it. To recap what I just said, as well as what we saw last chapter, we're going to be searching for points where the derivative is equal to 0, because that will indicate the possibility of a local maximum or a local minimum. Of course, it's not a guarantee. It might just be flattening out momentarily. But we also need to check the endpoints, because an endpoint might be the global maximum, even though we can't find the derivative equal to 0 there. And also, again, not likely to happen in IB, but technically we could have a function where the derivatives actually does not exist. That could still be a minimum or a maximum as well. Our plan, once we find those particular x values where the first derivative is equal to 0 or maybe doesn't exist, the way we're going to identify whether that point is a maximum or a minimum or simply a stationary point of inflection is to do one of two things, and it's kind of your choice how you want to approach this. You're either going to use what I learned as the first derivative test. Our book calls it the sign diagram test, but same thing. If you find out that the first derivative is 0 at a particular point, you can then just draw out a sign diagram for the first derivative, and if you find that it changes from positive to negative, then you've got a local maximum. If you find out that it changes from negative to positive, you've got a local minimum. It's the kind of stuff that we talked about in chapter 19. Nothing new. Your second option is what we call the second derivative test. So you just found out that the first derivative is equal to 0. So just calculate now what is the second derivative at that exact point. If you find out that the second derivative is negative, then that means that your graph is concave down, which means that you have a local maximum. If you find out that your second derivative is positive, then your graph is concave up, which indicates that you have a local minimum. If your second derivative is equal to 0, then that means that you had a point of inflection of one of those two varieties, so it's neither a min nor a max. I don't know that it is ever advantageous to use one of these methods over the other. I can't think of any examples where I'd really want to use one in particular, but there you go. It's your choice. Here's our plan for optimization. This is generally what we're going to do for every single problem. Again, every single problem is different. If we can draw a picture, we want it. We're going to need to figure out what the formula is that we need to optimize. It will not always be given in the problem. Sometimes it'll just say, hey, find the minimum amount of time it takes to do something. Find the maximum profit based on how many whatever are being sold. You might need to figure out what that function is. And then we're going to, step 3, find the first derivative, set it equal to 0. That'll get us all the points that we're going to test. Use either your first derivative test or your second derivative test. And then also check the endpoints, because those might be higher or lower than one of the maxes or mins that you just found. The book is referencing something that they call the graphical test. That's just like if you had a calculator graph it. But I mean, if you have a calculator, then this is a very easy problem, and you should have been able to figure out how to do this with a calculator months ago. You graph the thing and calculate the maximum or whatever. And then, you know, most of you don't like to do this, but yeah, you should write your answer in a sentence and specifically answer the question in context and all that good stuff. So I'm just going to do 2 examples here, 2 kind of like classic ones, just to illustrate the process. So when I think optimization, this is one of the classics that always comes to mind, finding a rectangle of maximum area given a set perimeter. Some of you might already know the answer to this. So spoiler alert, it's a square, and that should make some degree of sense, right? I could have a really, really long, narrow rectangle, and that's going to have relatively small area. Really, the longer it gets and the shorter these 2 sides get, the smaller the area is going to end up getting, because those 2 sides are getting closer and closer to 0, really. So having a more, I don't know, balanced rectangle kind of makes sense as having a larger area, but now we're going to prove it using the wonders of calculus. So we have a generic rectangle. It has side lengths of x and y. We know, however, that 2x plus 2y is equal to 100, which means we can rewrite y as 100 minus 2x divided by 2, or 50 minus x. That makes the area of this rectangle x times 50 minus x. You might see this written as area of x. And that's because this is the area as a function of whatever this side length is. And we want to maximize that area. How exciting. I could use the product rule here, but it's probably a little bit easier to just distribute first. So a of x is going to be equal to negative x squared plus 50x. We could take the derivative at this point. A prime is equal to negative 2x plus 50. We set that equal to 0, and then we're going to get that x has to be equal to 25. But if x is equal to 25, then since this is 25 here and 25 here, that's 50 out of our 100. The other 2 sides have to be congruent. They're also 25. Oh my gosh, it was a square all along. And of course, we could have also looked at that as that's a parabola, right? Where is its vertex? Negative b over 2a. In this case, that's 50 divided by 2, which is 25. So you could get your x value in that way as well. So there, one example of optimization. That wasn't too bad. The hardest part, I think, is just figuring out what the function is that you need to use. So for the second one, this is one example of a classic type of problem. This particular problem is really famous, or got kind of famous in 2015. This problem was on the Scottish Qualifications Authority, SQA, their higher level math exam, I think. So I don't know. I saw this problem show up in like my Facebook feed and stuff because I follow mathy things. The kids were complaining that it was too hard of a problem. But I don't know. I looked at it and I said that's just a very straightforward optimization problem. In fact, it's really nice because they even give you the formula that we're going to eventually optimize, which was rather nice. But anyway, let's pause the video, take a minute to read this, and then we will discuss. Okay, so our hungry crocodile is going to swim a little bit, then he's going to run. Do crocodiles run? I don't know. Towards the zebra and maybe catch it. And we've got a function telling us how long it's going to take, depending upon how far this distance is. So what is the time taken if the crocodile does not travel on land? In other words, if he just swims the whole way. If he swims the whole way, well, okay, what does that make x equal to if he swims the entire way? Well, then x is going to be this whole distance. That's going to make x equal to 20. So this first problem is really just t of 20. We pop that in. This first term is going to drop out to 0. That's great. So we're looking at 5 times the square root of 436. That's going to be about 104. Wait a second. What's the unit, though? Here we have t measured in tenths of a second. Why don't we just say that that's 10.4 seconds then? So we move on to Roman numeral 2. Now we have the crocodile swimming the shortest distance possible. If it swims the shortest distance possible, that means it's going to swim right over here, and then it's going to run the rest of the way. So what is x in this case? Well, now x is going to be 0. So we've got t of 0. Putting in 0 for x, that's going to be 5 times 6, that's 30, plus 80, that's going to be 110 or just 11 seconds. So not really a whole bunch of a difference there. And actually, this might be a good moment to just rewind for a second. Some of you might have been wondering where this function even came from. So keeping in mind that time is equal to distance divided by the rate, you can kind of spot here that 20 minus x, that's the distance that the crocodile is going to be running on land. And root 36 plus x squared, that's the distance that the crocodile is going to swim. So actually what this formula tells me is that the distance across the river is actually 6 meters, and its speed, its rate of swimming is 1/5, whereas its rate for running is 1/4. So it's actually because we have 5, which is going to be 1 over the rate, and 4, which is 1 over the rate. So we see that it's faster at running than it is at swimming, which I would not have guessed, but I don't know anything about crocodiles, I suppose. It's faster at running, but we are balancing that out with minimizing the distance that it has to travel. We know, this is clearly the shortest distance, but it's faster on land than it is in the water. So that's where the optimization problem comes from. That's why we have a problem here at all. Obviously, if it was a faster swimmer than a runner, then it would just swim directly to the zebra. There'd be nothing special about this. But anyway, I digress. Let's now answer the final question. So between these two extremes, between running a distance of 20 versus running a distance of 0, there's actually a fastest time, a minimum time taken for the crocodile to get to the zebra. What is it going to be? Well, we have the function t of x, and we're going to differentiate it, and that shouldn't be too hard. That's going to be 5 over 2 times 36 plus x squared to the negative 1/2 chain rule. We multiply by 2x, and then we're going to add, let's just say it's minus 4. Yeah. And then we're going to set that equal to 0. It would be nice to just rewrite this a little bit. Let's see. The 2 and the 1/2 can cancel, so that's going to give us 5x over that, and then minus 4. setting that equal to 0. Adding the 4, multiplying by our square root brings us here. Then we're squaring both sides. And then combining our like terms, we distribute the 16, subtracting 16 from 25 gives us 9x squared, which is equal to whatever 16 by 36 is. I don't care. X squared is 16 by 36 over 9. We take the square root of both sides. X is going to be plus or minus, plus or plus. Try again, plus or minus. The square root of 16 is 4. Square root of 36 is 6. That makes 24 over 3. Oh, that's 8. Oh my gosh. So X is going to be a distance here in between 0 and 20. So we're going to ignore the negative. So that gives us X equals 8 is our distance. We scroll back up. We put 8 in here. That comes out actually very evenly to 98 tenths of a second, or 9.8 seconds. Now, clearly in this case, that is the minimum time because it's the only place where the derivative is equal to 0. It's the only place where the derivative could not exist. There's no way that I was going to divide by 0 down here. So I mean, clearly by comparing 9.8 with the two endpoints, which we already did earlier in this problem, 9.8 is obviously the minimum. That said, we could have taken a look at our derivative here and made a sign diagram. We had x equals 8. If we choose any point to the left of 8, we're going to get a negative value out. You may try that on your own. If we choose any value greater than 8, we're going to get a positive. So that tells me that our original function was a minimum. I could also take the second derivative. I don't really feel like that because this doesn't look terribly nice to differentiate again. So that'll do. But anyway, as I said, we already found the endpoints. So given that this is the only other option, it had to be the minimum. So there you go. There's two optimization problems. There are many, many more for you to try out, all requiring different geometric formulas and other stuff to work with. So let's get practicing.